In this video, we're going to look at how to verify, prove, or establish an identity. Those are some of the terms that you might see. And we'll be using the fundamental identities from trigonometry. So here's the ones we're talking about here. Tangent of theta is sine of theta over cosine. Cotangent is cosine over sine of that same angle. And then you have the reciprocal identities. Cosecant is 1 over sine, same angle theta. Secant is 1 over cosine. Cotangent is 1 over tangent, the same angle. And then the last three are the Pythagorean identities because of the form. Sine squared of the angle plus cosine squared of the same angle is equal to 1. We have tangent squared plus 1 is equal to secant squared. Cotangent squared theta plus 1 is equal to cosecant squared theta. There's quite a few identities that you're going to learn and work with during the course, but you start off with these basic ones, and then from these basic ones you verify other identities, you establish other identities. So that's going to be the focus of this first video on verifying trig identity. So you'll see something like, it might say verify the following is an identity. It might say establish the given identity. It might say prove that the following is an identity. So here I'm just saying verify that each of the following is an identity. So you can have an equation. This could be a polynomial equation, a trig equation, a log equation, whatever. But what's the difference between a trig equation, or just let me just say, what's the difference between an equation and an identity? An equation is true for some, but not all numbers in the domain of the equation, whereas an identity is true for all values in the domain of the equation. So as an example, we can look at, say, a very basic linear equation, x plus 1. Say x plus 1 is equal to 5. The domain of the equation is simply all the permissible replacements of the equation. Not that they make the equation true, but they're permissible. So here on the left side, we have x plus 1. I can plug in any number for x, and that's going to give me back a number. On the right side, I just have 5. So really the domain of this equation is all real numbers. All real numbers. But the only one that works, if you solve this equation at -1 to both sides, is 4. X plus 1 equals 5. The solution is x equal to 4, because 4 and 1 is 5. So that's an equation. Domain all real numbers, but it only has one solution. Now something like this, let's say x minus 1 quantity squared is equal to x squared minus 2x plus 1. On the right side, we have x minus 1 quantity squared. I can plug in any number for x and square it, subtract 1 from it, and then square it. That's going to give me a number. Negative, positive, doesn't matter. On the right side, you can square any number. You can multiply a number by -2, add 1 to that. So in here, I can add or substitute any value for x, and the right side will give me a number. So the domain of this equation is any number. In this particular case, though, this is an identity because the statement that I have here is going to be true no matter what number I plug in there. If I put a 0 in there for x, I get the same number on both sides. If I put a 1 or x on both sides, I still get the same number because all I'm doing is squaring this. So these two sides are identical. Okay, that makes it an identity. The domain is all real numbers, and all real numbers will satisfy this particular equation, therefore it's an identity. You can say the same sort of thing if it's a trig equation. Depends on the domain. So let's look at the first one. I want to verify that secant of x times sine of x is equal to tangent of x. So generally what you want to do when you prove or establish an identity is you want to start with one side and show that it gives you the right side or the other side. So start with the left side and then show that that gives me the same thing that I have on the right side. Or I can start with the right side and show that it gives me the same thing that's on the left side. So this one here, I'll do it both ways. So I'm going to start with the left side. So I got secant of x times sine of x. I want to show that that's the same thing as tangent of x. So this is, the right side then is your objective or your goal. I want to show that the left side is the same thing as the right side. Thinking back to the fundamental identities, we know that tangent of x is sine of x over cosine of x. Well, on the left side we have a sine. And we have a secant. But from the reciprocal identities that I showed you, you can go back to that, rewind the video, but secant of x is the same thing as 1 over cosine of x. So this equals to, okay, rewriting that. Now the sine of x, I need that, so I don't mess with that one. So that's just sine of x. I can put that over 1, okay, to make it more clear. So let's just multiply this out. I get 1 times sine of x is sine of x. And then on the bottom, cosine of x times 1 is cosine of x. And as we saw from the list of fundamental identities, sine of x over cosine of x is tangent of x. And the identity is confirmed or verified. So generally you want to work with one side only and show that it reduces or simplifies to the other side. I started with the left side. This one though can work either way, so let me start with the right side now. Okay? What you don't want to do is you don't want to work with both at the same time. You don't want to multiply both sides by something, okay? Because then you're assuming equality, and that's what we're trying to prove. We're trying to prove equality, so you don't want to assume it from the start. Tangent of x, and I want to show that that's the same thing as secant x sine of x. So let's start with what we know about tangent of x. We know that it's sine of x. Over cosine of x. Okay, so what do we have now? Now the objective or the goal is to get the left side. What do we have over there? Well, we have a sine of x. Well, look, I have a sine of x right there. So I don't want to mess with that one. So this is then equal to sine of x. And then I can rewrite this as 1 over cosine of x. But 1 over cosine of x, that's one of your reciprocal identities. So 1 over cosine is the same thing as secant of x. And then I got the sine of x. And it's confirmed. So that one's done. Either way, you can start with either side, but again, you want to start with one side and show that it reduces to the other side. You can use some algebra. In this case, I use basically the fundamental identities is what I'm using for the most part in this set of problems. Let's clear this. Go to the next one. Another thing that you want to know again is generally you want to start with the most complicated side. Okay, there's going to be some cases where you might have to use factoring of the numerator and denominator to simplify. Generally, if you have a fraction, you want to combine. So start either side And you could use the right side and show that it gives you the left side, but it's a lot more involved. So generally, you want to start with the most complicated side. So in this case, 1 minus cosine squared x over 1 plus sine x is more complicated than plain sine of x. So I have it written down. I'm going to start with the left side. So what do we get here? Okay, so 1 minus, so I want to write this over one denominator. So this one has a denominator of 1 plus sine of x, and the 1, of course, is 1 over 1. You want to write that as a fraction. So my common denominator, should be clear, is 1 plus sine of x. So of course, out of these two add fractions, we have to have the same denominator. So in this case, then, in order to have a 1 plus sine of x over here, I have to multiply the top and the bottom of this 1 over 1 by a 1 plus sine of x. So that's going to give me 1 plus sine of x. And that's going to be minus cosine squared x. So my objective again is to get the sine of x. So I don't need a cosine squared. Got a sine of x there. So let's go up here and say this is equal to, this is 1 plus sine of x. And then we have 1 plus sine of x. And then we've got this fundamental identity. We have sine squared of x plus cosine squared of x equals to 1. So since I want to wind up with a plain old sine of x, that tells me that I probably should get rid of this cosine squared. So let's do this. Let's rewrite this. Sine squared minus 1 equals to minus cosine squared of x. So all I did here is I took this main identity here, fundamental identity, and took the cosine squared over, that made it a minus cosine squared. Took the 1 over, that made it a minus sine. Other ways you could do this, so I'm just replacing this minus cosine squared by sine squared minus 1. So what do we have? We have minus 1 and 1. Those will cancel to 0. So that's going to leave me with, and this is an x here. That'll give me sine squared x plus sine of x. And that's all over 1 plus sine of x. So always be thinking of simplifying. What's my objective? I want to get a sine x. Well, see, I've got everything in sines here, but I've got too many. I just want one. So how can I simplify this? Again, you're going to be using a lot of algebra. If you're weak in algebra, then you're going to be weak in trig, because algebra is the foundation to trigonometry. So on this one here, I can factor out a sine. Of x. And what am I going to have left? This will be sine of x plus 1. Okay, I'm just factoring, just like if you had x squared plus x squared plus x. Factor out the x, you get x, and then parentheses x plus 1. The only difference here, instead of a plane of x, is sine of x. At the bottom, we still have the 1 plus sine of x. Okay, this is a factor by itself, 1 plus sine of x, and on top I have sine of x plus 1, but that's the same thing, right? Sine of x plus 1, the same thing as 1 plus sine of x, so these will divide out. And what does that give us? We're left with sine of x. And that's what we wanted. So that proves that this works. So this again is an identity, as long as that uses, of course, the domain of the equation. So obviously in this particular case, the domain is going to be all values of x that don't make this denominator 0. So it'll be all real numbers, or angles if you're working with degrees, that don't make this 0. Look at the next one. Sine theta over 1 plus cosine theta plus 1 plus cosine theta over sine theta is equal to 2 cosecant of theta. So we're going to try to show that the left side is equal to the right side. So in general, again, you want to pick the side that's more complicated. Because if you pick the right side, 2 cosecant theta, okay, how do we get all of this on the left side? Not that easy to go from 2 cosecant theta to what I have on the left side. So in that case, it should be obvious that I'm going to use the left side and try to simplify that down to 2 cosecant of theta. Now remember, look ahead and know that cosecant of theta is 1 over sine. So 2 over sine is the same thing as 2 cosecant theta. So always be thinking ahead. Starting with the left side, what's my common denominator? This one has a denominator of 1 plus cosine theta. This one has a denominator of sine theta. Has to have the same denominator. I can't add the numerators unless the denominators are the same. So common denominator is 1 plus cosine theta times sine theta. So look at the first fraction. What's it missing here? On the bottom, it's missing a sine. So I multiply the top and the bottom by sine, and I would get this, right? So sine theta times sine theta, that's sine squared. Theta. Let's stretch this out a little bit. And then on the next fraction, the denominator has to have a 1 plus cosine theta and a sine theta. Well, it has a sine theta, doesn't have a 1 plus cosine theta, so I need to multiply that numerator by 1 plus cosine theta. So it's 1 plus cosine theta times 1 plus cosine theta, or I can write that as 2 factors squared. So now I'm starting with the left side, and my objective is to get the right side. So up here then is equal to, and I have my denominator. And for right now, I leave the denominator factored out like this. In some cases, you might want to multiply it out, but you always look into, we know we got to get just this 1 one term times 2. Cosecant theta times 2. So we know something has to cancel out, so we might as well leave it as a factor. So this will be cosine theta times sine theta. Remember, I told you that 2 cosecant of theta, that's the same thing as 2 over sine. Two over sine of theta. When you look at this denominator, I have a sine theta right there. So that pretty much tells me that somehow the stuff that I'm going to have in the numerator is going to have to simplify so that the 1 plus cosine theta cancels. So all I have to do up here then, I have the sine squared theta plus 1 plus cosine theta squared. So that's just like squaring a binomial. Squaring a binomial. A plus b times a plus b is a squared plus 2ab plus b squared. Same sort of thing here. This will be 1 squared will give me that. And then twice the product. Here, I have 1 in cosine will give me 2 cosine theta. Just that a little bit. And then plus cosine squared theta. So again, x plus cosine theta squared gives me 1 plus 2 cosine theta plus cosine squared theta. Use the formula for squaring a binomial. That's just some basic algebra. And now let's look at what we have in the numerator. One of your basic identities, fundamental identities, tells you that anytime you have the sine squared of an angle plus cosine squared of the same angle, that's going to give you 1. So sine squared theta plus cosine squared theta is 1. And then we have another one over here, so 2 and 1. I'm sorry. 1 and 1 is 2. So sine squared theta, cosine squared theta is 1. And then I have this one right here, so that's going to give me a 2 plus 2 cosine theta over 1 plus cosine theta sine theta. Now, mentioned that we somehow had to cancel this 1 plus cosine theta in order to wind up with this over here. Well, factor 2 out of this. Factor out of 2 from the numerator. That give me a 1 plus cosine theta over 1 plus cosine theta parentheses sine theta. So here I have 1 plus cosine theta and a 1 plus cosine theta in the denominator. Close this parentheses here. These would divide out. And I'm left with 2 over sine of theta. 2 over sine of theta. But 2 over sine theta divided over here is equal to they put the 2 here this way, and then this then will become 2 1 over sine theta, just to make it clear. So these divided out, so that leaves me 2 over sine theta, which is the same thing as 2 times 1 over sine of theta. But 1 over sine, that's from your reciprocal identities, is cosecant of theta. And that confirms the identity. So we're using the fundamental identities from trigonometry to prove these identities, or prove that these are identities. We're using some basic algebra. You have to know how to find common denominators. Instead of x's and y's, it'll be trig functions, sine, cosine, cosecant, whatever. You start with one side. Generally, you want to pick the more complicated. Now, in some cases, it might not be that way. If it's a formula that you see will equal to the other side, that might make it a little bit easier. But generally, you want to pick the side that's more complicated. If it's a fraction, you might have to combine, find the common denominator, and then show how that simplifies to the right side. Or in some cases, it just might be one fraction that you can factor, cancel factors, and that will simplify to the other side. So as I go through these, I'll point out the different scenarios that you can have. But in this case, that concludes the video. Thanks for watching, and we'll see you next time.